This is day 2, video 1. We're going to talk about increasing, decreasing, and concavity, general shapes of function behavior. Skill and drill mostly. The next video will get into some of the applications. So recall an increasing function means as x increases, f of x increases, meaning as we go left to right, the graph goes up. So we could have left to right going up like so, like so, like so. Goes up as you travel left to right. Decreasing function, as x increases, f of x decreases. So as you go left to right, the graph goes down like so, or like so. Concave up, like a bowl that is right side up. A function can be concave up decreasing, or a function can be concave up increasing. So notice it looks like the left side of a bowl that's right side up, or it looks like the right side of a bowl that is right side up. Concave down, a function can be increasing concave down, or it can be decreasing concave down. You notice it looks like a bowl that's upside down. To be concave down, it looks like a piece of the bowl that's upside down. In general, you should certainly be able to sketch a graph of a function if you are told it's increasing, decreasing, and its concavity. You should also be able to look at a graph and describe if it's increasing, decreasing, and describe its concavity. So you should be able to fill in these following 6 things at any time. So a graph that's increasing and concave up. So as it goes left to right, it's going up, and it looks like a bowl that's right side up. Increasing concave down. As we go left to right, it's going up, and it looks like a bowl that's upside down. Increasing at a constant rate. So that's a line, straight line. Constant rate of change. Slope is constant. Decreasing concave up. As you go left to right, the graph goes down, but it looks like a bowl that is right side up. So like that. Decreasing concave down. As you go left to right, it's going down, but it looks like a bowl that's upside down. Decreasing at a constant rate. That should be a decreasing line, straight line. Page 2. Local maximum point means in its little local region, it's the highest point on the graph. So in its little local region, the maximum point may be like so. It may be, for example, a pointy graph like so, maximum point right there. There's also other situations you can have a weird sort of graph like it's going up, reaches a peak, and then suddenly changes and drops down. So this point up here would be a local maximum. But generally, we're going to see this first one, so the types of functions we deal with most of the time in this course. Similarly, a local minimum in its local region, the very lowest point on a graph. So for example, graph like so, the very lowest point on the graph there, local minimum. Or it could be a pointy graph like so, the very lowest point on the graph is there. Or again, something weird and strange like it's going down, 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 reaches a low point and then suddenly changes and bounces up here. This point down here is the local minimum. An inflection point is a point on a graph where the concavity changes. And let me draw a few different examples. A graph could be increasing concave down, then change to increasing concave up. So that point where it changes concavity is the inflection point. Similarly, it could be increasing concave up, then change to increasing concave down. The point where it changes concavity is the inflection point. Another example, it could be decreasing concave down, then it could change to decreasing concave up. The point where it changes concavity is the inflection point. And lastly, it could be decreasing concave up, then change to decreasing concave down. The point where the concavity changes is the inflection point. Now, in these two examples in the middle, the inflection point is the point where the graph is steepest at the inflection point. And the two on the outside here is where the graph is least steep. We'll come back to that idea when we see some applications of the importance of inflection points, point where it's steepest, point where it's least steep. End behavior, tail behavior of a function. Now, in a traditional calculus course, we spend time on this concept, writing it in limit notation and so forth. But in this course, we're mostly going to focus on the importance of the tail behavior, usually on the right side. What is the function's behavior as the x value increases to infinity? We're asking, what is the height of the graph on the tail? Does the graph diverge to infinity? Does it diverge down to negative infinity? Does it flatten out to a certain fixed y value? We're asking what y value does the function approach, or does the function diverge to infinity, negative infinity? So let's look at a few examples. So for example, this is what's called a logistic function. So it looks like over here, it's flattening out. Let's say it's approaching a height of 150 over here. And on this end, it's approaching the x-axis. All right, so the right tail end behavior is that this function approaches y equals 150. So as x diverges to the right, as x gets bigger, 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 as you walk to the right, the graph gets closer, 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 closer to y equals 150. The left tail end behavior is that the graph gets closer and closer to y equals 0. So again, as you walk to the left, the graph gets closer and closer and closer to a height of y equals 0. Another example, on the right tail, the end behavior, we see that the function goes down, 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 down towards negative infinity. We're saying as x gets higher and higher and higher, as x goes up, as x diverges to infinity, the y values plunge down towards negative infinity. The right tail end behavior is that y approaches negative infinity. The function diverges down to negative infinity. On the left tail, as x goes to the left, the function goes up, up, up. So the left tail end behavior is that the y diverges to positive infinity. Let's look at one more. This looks like a decreasing exponential function. Decreasing exponential function, the right tail behavior as x goes up, 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 as we walk to the right, the y approaches 0, right? The height of the graph is getting closer and closer and closer to the x-axis. The left tail behavior, as we walk to the left, the height of the graph goes up, up, up. The y approaches positive infinity.